Here's the next group of VSEPR shapes that all kind of go together. These three are based on the tetrahedron. They all have 4 regions of negative electrons on the central atom. Now those may be 4 bonding regions, or they could be a combination of bonding and non-bonding electron regions. But they're all going to be kind of based on this tetrahedral structure. I'm hoping that these 3 shapes are also familiar to you. I think most first-year chem kids have seen these tetrahedral shapes. For example, I think the Lewis structure of methane should be something that we could do forwards, backwards, upside down, inside out. It's pretty simple. Carbon loves to make these tetrahedral structures where there are 4 regions of electrons on the central carbon. All 4 are bonding regions. They want to repel and orient themselves as far apart as possible. On paper, it looks like they're 90-degree bond angles. And that structure is totally acceptable for a Lewis structure. The Lewis structure does not need to be drawn to the true 3-dimensional shape. But in your mind, when you draw that methane CH4, you really need to think of it as looking like this guy. So in class, we're going to look at those model kits so that you can put a tetrahedron in your hand and you can really experience the wonder of a tetrahedral structure with 109.5 degree bond angles. We must know that number. 109.5, the bond angle in a tetrahedron. It kind of looks like a little rocket ship. Now again, it's okay to draw the Lewis structure as I have it drawn. That's 1,000,000% acceptable. But then if they say, hey, what are the bond angles? You better not say 90 degrees. 109.5. I have seen questions too where they might say draw a rough sketch of a ball and stick model. And then I would kind of sketch something that looks like this picture. They want to know, in your mind, do you really know what a tetrahedron looks like? Everybody can say, oh yeah, it's tetrahedral. Tetra means 4, so everybody gets this one right. But do you really know what that structure looks like? So they may ask for something like that, but they're not going to have you draw the Lewis structure to 3 dimensions. They might just say, draw a ball and stick model in 3 dimensions, a rough sketch of a true tetrahedron. Okay, so based on the tetrahedron, we're going to have the trigonal pyramid. So again, trigonal makes you think 3. There's 3 of something. Another easy Lewis structure would be ammonia, NH3. Everybody draws this one right. And again, we've always said those extra lone pairs are so important. They affect the shape, and they obviously show that nitrogen has an octet. So if you look at the central nitrogen, there are obviously 3 bonds. So those bonds represent regions of negative electrons. But there's also a 4th region of negative electrons. That lone pair. So you've got a total of 4 regions of electrons. So in your head, you're thinking that tetrahedral rocket shape. But that 4th region is not really an atom. That 4th region is the lone pair. But can you kind of see how that looks similar to a tetrahedron? Similar bond angles? That's why it's called a trigonal pyramid. It's not flat like the trigonal planar. And again, this is something that they'll do maybe even a multiple choice question to try to trick you. By formulas, they look really similar. What if you had BH3 versus NH3? Those formulas look very similar. But once you draw the Lewis structure, they're very different. The boron structure was a flat triangle, a trigonal planar with 120 degree bond angles. With the addition of that lone pair on top of the nitrogen, it changes the shape. Instead of being flat, it's a pyramid, trigonal pyramid. The bond angles are, here they're listed as 107.5, or you could say approximately. 109.5. Or you could say slightly less than 109.5 degrees. I mean, obviously the 107, that's impressive. If you know 107.5. Or you could say approximately or slightly less than. It's based on the tetrahedron, which would have the 109.5 degree angles. But again, we kind of mentioned in the last video that a lone pair seems to take up more space. So it kind of smushes the other atoms. So those bond angles of the existing atoms are a little bit less than what you might originally expect. Same thing happens with this second bent structure. So there are two bent shapes. In real life, they're very similar. A bent structure has two atoms and then either one or two sets of lone pairs. So the formula may make it look like it could potentially be linear. Or when you draw the Lewis structure, it could potentially look linear. Like often people will draw this water Lewis structure, as I have written down here. They may draw the Lewis structure looking kind of linear, which is 1,000,000% acceptable. If the question says draw the Lewis structure, that's fine. But then you better not say that it's linear. Because now when I do the VSEPR shape, I'm taking inventory of not only bonding groups of electrons, but also non-bonding electron pairs. So in a bent structure, you'll have two bonding regions and either one or two lone pairs. Now, obviously, they're going to have you draw the Lewis structure first. And then they'll probably say, what's the shape? I'm going to say bent. They might ask me to draw like a rough sketch, a ball and stick model. And then they might ask me for the bond angles. Now here we've got two lone pairs in these extra positions. So this bent structure is actually based on the tetrahedron, where there's 4 bonding regions. So technically, the angle is 104.5. Or you could say, again, approximately 109.5 or slightly less than. Less than 109.5 degrees. Now the other bent, the bent that was based on the trigonoplanar, that one's going to have bond angles that are slightly less than 120. So that's, you have to be a little careful that you could have two bent structures that, they have the same shape, the same name, but the angles are a little bit different. So you have to be aware of that. This bent, the angle is actually even a little bit smaller because there are two regions of lone pair electrons. So again, I'm hoping that these 3 shapes are, again, familiar to you. They're all based on the tetrahedron, so you really have to picture that 3-dimensional tetrahedron in your mind, and then as you add lone pairs, picture yourself like taking off one of the atoms of a tetrahedron so that you can really visualize a trigonal pyramid. Oh, it is like a little triangle pyramid in 3 dimensions. Or if I have 2 regions of lone pairs, what I'm left with is really a bent shape. It's not linear.